Maybe I have to motivate my discussion with an example. Is there anybody in this room who's willing to tell me what that looks like? Can you just tell me the shape of this curve?
It curves up.
Always. Which one? Oh, so you're saying this curve doesn't look like anything. It's a collection of curves. And if C is positive, well, actually, I misspoke. Let's see B1. Piece of cake. That's exactly what it looks like. It's a standard natural exponential function. But if C is bigger than 1, I think the curve looks something like this. It's what I have in import, but pulled away from the x-axis by certain factors. I think if C is between 0 and 1, it's my same darn standard natural exponential functions graph, but compressed towards the x-axis by a factor of whatever. And if C were negative, I think I get the same darn images, but mirror images through the horizontal x-axis. I think what I have with that equation is a whole family of curves, albeit they all seem to have a horizontal asymptote on the x-axis. So here's my new question. Can you and I find a whole other family of curves that has the following quality? If one of the members of the other family crosses at that point, do it in such a way that tangent lines are perpendicular. Now, as this one solution, or one curve I should say, not solution, in red continues, I want to be able to hit the next curve at another right angle. It means I'll be perpendicular to it. And maybe with all the other curves as well, I'm going to hit them at right angles. I want to be able to find a collection of these other curves. I'm going to refer to these as orthogonal trajectories. I'm being a little too sloppy, I'm sorry. I'm trying not to give away what they all look like. So question, if I give you one family of curves, can you generate the entire family of orthogonal trajectories to my given black family, which will be drawn in red? And I maintain we can do it easily. After all, if this red curve and the black curve, I know I made a mistake, it looks awful. It doesn't look like they're tangent lines meet at a right angle, my apologies. But if they do, I think the slope of one tangent line is related to the other. That's too much thinking. Think math deep. Two lines are perpendicular. What's the relationship of their slopes? They're negative reciprocals of each other. Well, when you look at the black curves, did I tell you what their slopes are? Oh shoot, I didn't. You're right. Let's generate them. I think to generate the slopes of the curve in black, I'm simply going to differentiate. Life is that easy. Would you guys agree? However, I have to confess that C is kind of complicated. So if you guys don't mind, can I look at the original equation and solve for C? And with the original equation solving for C, I think C is going to be nothing more than y over, whoops, I've lost it. I can't do my math D. Is that y over e to the x? All right, let me make a substitution. Replacing C with y over x, I guess that means dy dx is equal to 1. However, since I'm trying to find a family of orthogonal trajectories, notice how this is simply describing something in terms of the black curves. Now to describe the slope of tangent lines to the red curves, I'm going to dive in and consider dy dx for the other curves in red to be negative reciprocals. Good. Are the derivatives for the curves I initially drew in black. And that being the case, I will multiply both sides by y to bring it to the left-hand side. And I can get my arithmetic straight. That is a negative 1. But don't you guys agree on the left-hand side? What actually should I differentiate with respect to x to get y? I mean, what is up here that's got the quality that when I differentiate, I get a y? What was that? Anybody, please? Oh. You guys, what's up here in my hand that I would differentiate to generate a y? 1/2 y squared. You guys, if you're nervous, I'll close my pen. You double check me. To differentiate this, yes or no? Do I get a y? See, I think this is no. I think if I differentiate this with respect to x, I get a y times chain rule says dy dx. Oh shoot, check that out. It's exactly what I have. And now to undo the differentiation process with respect to x, I think I'm left with the 1/2 y squared being equal to negative t. Sorry, I said t, I meant x. My goodness. And negative x plus some constant integration. Can you see once I've already used c in my equation? So you guys humor me with this. What do these curves look like?
I'm a little confused here.
Yes.
Just at the beginning there, where you've got y over e to x equals c. So you would have to integrate that, right, in order to solve for c. But wouldn't there be a second
I don't think solving
constant?
c has anything to do with integration here. Besides that, if you integrated both sides with respect to x, aren't you going to get what I started with?
Oh, okay. I wasn't. I
I was
didn't see that
simply
over there.
saying,
All right.
once I differentiate, let's see if I can describe c in terms of x and y. Oh,
Yeah.
yeah, over there with the original relationship. I guess I can.
Yeah, I just wasn't looking at
And I
that.
made a substitution. Okay, you guys are making me nervous. What do these look like? I'm serious, this is Math B. What do these look like?
Parabola.
Parabola is opening up or down?
Sideways.
Good, I think going this way. Oh, thank goodness. That seems to be the case in my picture. They seem to be parabolas opening this way. So I guess with my family, we're orthogonal trajectories. If I try to draw it in, I'm going to do a lousy job, but I guess I'll give it a shot. Again, doing a lousy job. Sorry. You guys okay with that? Let's try a different one. How about if I consider trying to generate the orthogonal trajectories to, how about something that's looking like this? What do these look like? Hyperbolas. Very nice. They're standard hyperbolas. I shouldn't say standard, sorry. They're hyperbolas. Branching out left and right or up and down? Left and right, left and right. Always. Depends on C. Thank you. So C is positive, I think you're right. I'm branching out left and right. But if C is negative, I think I'm branching up and down. So I've got a whole family of those curves going on. So to generate your orthogonal trajectories, let's do what I did before. Let's talk about dy dx. I think to come up with dy dx, I'll simply treat y as an implicitly understood function in x and differentiate, again, implicitly with respect to x. To do that, I should hear my voice again too much. You talk.
2x minus 2y dx.
Oh shoot, I'm going backwards with my examples. I guess it's an easier example than my first one because through the differentiation process, my constant c dropped out. I don't have to play any algebra games. That being the case, to isolate dy dx, doesn't that tell me that dy dx is equal to, I really have no idea, is that x over y? You guys help me with this. In English, I want a yes or no answer. In English. Does this represent slopes of tangent lines to my original family of curves, which are hyperbolas? One yes.
Yes.
Okay, 2 up to 3. Now I like 3, it's a nice prime number. So I agree with that. But if this is describing slopes of tangent lines to the original family, I haven't answered the question. I want to generate the family of orthogonal trajectories. So if you guys don't mind, I will now create a whole new differential equation in which dy dx is of very nice. Or shall I say that my 1 over y dy dx is equal to my negative x?
Yeah.
Did I write it? Say yeah.
X over y.
My apologies. Thank you. That was my math error. Is that better? Still not better. You mean the original one was wrong? My goodness. Can I fumble back? I meant to say, well, I did say it in English, I didn't write it,
Right.
that we now want to consider the negative reciprocal of these slopes. Ay, ay, ay. Let me fix my horrible mistake. That means, does that give me 1 over y? Is that what I had in my last example? No, I don't think it was. So do you guys think, instead doing something to both sides equal sign, like in my last example, do you think you could tell me what the heck you would differentiate with respect to x in order to generate what you have on the left-hand side? I can't hear you. This two can't hear you.
Natural log of y.
Natural log of.
Absolute value of y.
Thank you. Because y could be negative. And that being the case, shoot, life's a piece of cake now. Let's just, you and I dive in and anti-differentiate with respect to x on both sides. And I think on the left-hand side, undoing the differentiation process with respect to x, I just land at the natural log of the y. But to undo the differentiation process on the right-hand side, in other words, integrating with respect to x, would you guys not agree? Oh, hold it. I put a C there. I didn't mean that. I meant C1. I was saying constant. I started. Were you guys able to solve for x? Please tell me. Somebody. Really? I feel so alone.
Natural law.
Blood's bursting out my arm. C2. X? Oh, yes, no.
Wouldn't it be e to the x?
I'm sorry, I did make a mistake. I apologize. My apologies.
Oh.
That was fine, I guess.
You guess. Really? So, okay, do I need to show more steps?
I'm just unsure of where the C2 came from.
I'll come back to what I had. I
Okay.
promise I'll get the same thing. Excuse me. I'm going to exponentiate both sides. My goodness. I'm going to use my math D skills to clean up the right-hand side.
Oh. Okay.
Get a tad bit of cancellation here. E to the C sub 1 is just a constant, I'll call it C2. But here with this factor, that's the E to the natural log of 1 over the absolute value of x. And now I can perform a tad bit more cancellation. Whether x is positive or negative, I guess I can just say C is going to be positive or negative. I'll just call it C3. Graphically speaking, what do these look like? I'll ask that again. Graphically speaking, what do these look like? What's hyperbola? Oh, whole collection of hyperbolas. It's just this time the asymptotes are not diagonal, the asymptotes are on the axes. And so I guess with the original family, where for orthogonal trajectories, that kind of look like this. It seems to me that with what I just found algebraically speaking over here, the family of orthogonal trajectories are hyperbolas with the x and y axes as their asymptotes. Okay, you guys, I'm a little off again with my picture. I know I can't draw, but the idea is the red curves and the black curves should be meeting each other at right angles, meaning where they do intersect, their tangent lines themselves are meeting at right angles. So maybe not ground shouting, but it's just a gimmick for you, for the author and I, to slip in this notion of solving PEs. If you guys are upset with me in playing this goofy game of rewriting this way, you don't have to. You don't have to listen to me because in about 2 minutes I'll give you an alternative.
So are there graphic calculators that are capable of doing these?
What a question. I don't know. If any of them do, it would have to be the 89, the 92, or the new one beyond the 92. I forget what it's called. I think it's the Explorer.
Okay.
Brad, I'm just being honest. I never thought of checking it.
Okay.
You can, you just have to make a program that you can do.
Oh, so you do have to write a little program.
Yeah, I don't think there's one built in for doing that, but it has all the functions that would be the steps of it. So,
I can see that. I can see that. I've used other technology to generate these, but not with the calculator. But I do believe You guys, come on, hit me up. Anything on the board before I erase it?
Yeah.
Yes, sir.
I'm a little confused on how you went from, I guess, the top of the right board to the next step. Like,
You mean from here to here?
Yeah, how'd you get rid of the e's?
It was this easy. When it comes to this factor right here, this is nothing more than a constant. There are no x's and y's. I just give it a whole other name. I call it C2. And sir, to be clear to you, the reader, I should have stated that. I should have said, oh, where C2 is a whole new symbol I just made up out of thin air, but I'm just using it to replace E to C1 because it looks simpler. Now, I think when it came to getting rid of the E here, that's different. I'm now composing a natural exponential function with a natural logarithmic function, but through composition they undo each other. They give me the input right back. And sir, I so wanted to do it here, cancel, but I couldn't, because the negative sign's in the way. I had to throw it upstairs as an exponent first. Now this composition undoes itself. And I get the input right back. I hope you guys aren't this quiet for the whole semester.
I tend to disagree with you that after 1 is wake up time.
After
Half of us in this class have been sleeping all day during the summer.
You know, you got a good point. There is a difficult transition, isn't there, from summertime? I wasn't sleeping. I was here. But I see your point.
Or you're a college student. You're a college teacher.
I know, but I'm at the college. I fit in some common category. Well, you guys. Check this out. I want a yes or no answer. Is that a differential equation?
Yes.
I told you in 5 minutes I'm going to give you an alternative technique. I misspoke. It's going to take me longer than that. I'll have to see how it goes. You know, I want to do something a little bit different. Instead of solving this differential equation, I want to talk about its solutions, but from a geometric perspective. And from a geometric perspective, I think there's a lot I can say right now off the top of my head. After all, if this is the x-axis, this is the y-axis. You guys, humor me for a minute. Can I put in a few ticks? If my solution passes through the point 1, 1, look at my differential equation. What can you say about that solution?
Zero.
What's zero?
Slope is zero.
So the line.
Of the original.
Everywhere? Everywhere?
At that point.
Oh, that's different. I think what I can say when I plug 1 in for x and 1 in for y is that if the solution to this differential equation passes through this point, the slope of the tangent line is horizontal. I misspoke. The slope of the tangent line is 0. The tangent line itself is horizontal. Let's keep going. I think if my solution passed through the point 1, 2, plugging 1 in for x, 2 in for y, doesn't that mean y prime is negative 1? So if the solution passed through this point, I think the slope of the tangent line at that point is going to be negative 1. If my solution passed through the point 2, 1, that means y prime is positive 1. And there's going to be the tangent line to the solution of my differential equation if it does indeed pass through the point G1. Do you guys mind if I finish the rest of the sentence? I can probably get it done in a half hour. Do you guys see my point? Isn't this a lot of work? I think what I'm trying to do is build something called a slope field. And so that I can get through an example or more than one example in 30 minutes, I claim defeat. I'm not going to finish the picture this way. I'm doing something completely different. I want to build a slope field, but I'm going to use what I call isoplanes. This is a terribly sophisticated, or should I say, sorry, I take it back, terribly slick, but not complex technique for building a slope field. Excuse me. So I'm going to build myself a nifty little table. And I'm going to pull out of thin air just numbers for y prime. I'll make it, how about a negative 2, a negative 1, a 0, 1, 2. And I'm going to generate the corresponding, what I refer to as isoclines. And in building the isoclines, here's what I'm going to do. I'm going to plug -2 in for y prime. Let's solve for y. If I do, I think it tells me that y is equal to x plus 2. Do you guys agree? Please double check my arithmetic. But what it tells me, graphically speaking, in the xy coordinate plane is the following. X-axis, y-axis. Allow me, you guys, a few tips. If I draw that green line, y equals x plus 2, here it is. You guys, listen to my sentence in English, and you finish it. If any solution to the differential equation passed through that green line, what would be the slope of the tangent line? -2. I agree. I just generated a lot of ticks all at once. Any solution passed through that isocline is going to have a slope of -2. But you know, if I plug -1 in for y prime over there, that tells me I get the isocline y is equal to x plus 1. And who the heck cares? We do. Because if any solution passed through this particular line in green, it's going to be the case that the slope of the tangent line at that point is going to be -1. So if you guys allow me to draw the line y equals x plus 1, here it is. The slope of the tangent line is going to be -1 for any solution passing through that line. Next, if I allow y prime to be 0, oh, that's nice. I get a nice clean equation in green, namely y is equal to x. Oh, here it is. Pass through the origin. It's just that, yet again, if any solution passed through this line, it's going to have a slope of a tangent line to be equal to 0. The tangent line is going to be horizontal. You guys, can I just do 2 more? If y is equal to 1 or y is equal to 2, my isoclines become y being equal to x minus 1 or y being equal to x minus 2. And when it comes to y being equal to x minus 1, if any solution passed through that isocline, the slope of the tangent line is, oh, look at that. It's the same as the slope of the green line. And one last one. Y being equal to x minus 2. If any solution passed through that isocline, the slope of the tangent line is actually positive 2, steeper than the green line. You guys, look at how many ticks I just created for my slope field. I think that's so much more effective than just clunking around, plugging certain numbers in for x and y into the original differential equation. By the way, when it comes to test situations, I won't allow it any other way. I'll be clear with my instructions. I'll ask you guys to give me the slope field by looking at some isoclines. And I think that might be enough information for you not generating some solutions. Yes, sir.
So when we choose the initial, the left column for the y prime, do you just do that based on the function given y prime equals x minus y?
You know, technically speaking, sometimes I'm much more selective. I think this example is so darn easy that I just kind of gave up and chose value between -2 and 2. I think with my subsequent examples, I'm getting more sophisticated where you and I are going to intellectually think better what the y prime value should be so that my solutions come out nice. I'll illustrate that with a couple more examples. I'll be careful with them.
So, do you just want us to keep plugging in values until we kind of see a pattern, or?
If this were a test question,
Yeah.
that's what I'd expect.
Okay.
But like I said, with my next subsequent examples, I'll try to be more sophisticated to where you might have to think more clearly about how you're going to choose those values for y prime.
Okay.
Oh, I've used green, I've used red, I've used all my Christmas colors up. Put blue. Let's try to draw some solutions. What do you think? Sounds good to me. What do you think? So all these lines are the same. You know, unfortunately, when I'm doing this on the board, it looks really natural, but I am 100% wrong. And there's something really missing here. It's so important, I'm going to give it a name. I'm going to call this my existence uniqueness theorem for solutions to differential equations of order 1. So theorem. Given a differential equation of the form y prime being equal to some function f in 2 variables. In other words, it's a first order DE, and y prime is isolated on one side of the equal sign, and what's on the other side is I have no clue. Some function in 2 variables x and y. Given such a differential equation, if both f, okay, I need to show hands. How many of us have not taken math 32? 1, 2, 3, 4, 5, 6, 7. So help me with this. Differentiate with respect to x. X squared, what do you get? 2x. To differentiate with respect to y, y squared, what do you get? 2y. But what if I asked you to take something like an x squared, y squared, and differentiate with respect to y? Shoot. No, I can't, because that's not a function of a single variable. I have to change my notation. I'll change it. I might refer to this as a partial derivative with respect to x or y. I'll choose x. Because this is a function of more than one variable. But it suggests that I should treat y as a constant. Not only x is an understood variable for the moment. So treating y as a constant, what would this partial derivative with respect to x be? 2x y squared. What could you say about the partial with respect to y of the same darn product? So 2x squared times y, I agree with that. All it really means is in the x, y, z coordinate system, I may have some surface described this way, which is like a sheet in 3 space. It's just at a given point, I want to talk about how the z values are changing walk in the y direction, or how the z values are changing walk in the x direction. For those of you who have not yet had Math 32, this is what we're going to be discussing this semester. Or next semester, whatever you take in 32.
How far into the semester do we tackle this?
Farther than it should be,
Okay.
unfortunately, because it's a very light topic.
Okay.
So I never finished my sentence. Given this differential equation, if both f and the partial of f with respect to y are continuous about some order pair x naught y naught, then there exists a unique solution to my differential equation through that point, x naught comma y naught. You guys, you give a notation. This uppercase backwards E stands for the phrase
There exists.
there exists. With an exclamation point after it means there exists a unique solution. I'm not making this notation up. We refer to this as our
Universal quantifier.
existential quantifier. Yeah, you want to learn more about this notation, how to use it in combination with other symbols like that? It's called math. Math 15. And you guys, your author does not say this. He kind of breaks stuff into different parts. He says, oh, there's got to be some rectangular region about that point for this to be true. Nonsense. If both these are continuous about this point, it means there exists an open interval about this point, for which this is true, which means I can always draw a rectangle in there. So I think the way I'm stating it, the way he states are equivalent. I just think this is a bit more slick with my choice of words. So you guys check this out. My original DE, shoot you guys, I erased it, sorry. I'm in the middle of this example number 3, aren't I? Is that correct? 3. And my DE was this. I hope you guys, I'm sorry, I made it up, is that correct?
Yeah.
But if that's the case, isn't it the case that f of x y is equal to x minus 1? I want a yes or no answer. As a function of two variables, do you think this is continuous everywhere? See, I think it is. It's just polynomial, isn't it? I see it's linear. If I were to take a peek at the partial of f with respect to y, what would I get? I can't hear you. I still can't hear you.
Negative one, zero minus, or just negative?
Negative 1. Thank you. Because that is being treated as a constant, isn't it? Yes and no, is that continuous everywhere? Yeah, it is, which means I've got a 100% error in my example. Watch. I suggest this blue curve hits this line and stays on it. That can't be the case, because I think the line itself is trivially a solution to DE. Look at this line. It's y equals, actually I forgot what it is. Oh, shoot. Thank you, I lost track. It's this one. When you pick y, or pick x minus 1 off the import and slap it in here, what do you get? What do you get? I can't hear you. Positive 1. Thank you. You get positive 1, and is the slope everywhere on the line positive 1? Well, look at this line. Is the slope everywhere positive 1? Well, yeah, so I think trivially this satisfies my differential equation. It is indeed a solution. But if both my f and my partial for f respect to y are continuous everywhere, that means no matter where I am on the line, there's only going to be one solution, and I already have it. It's the line itself. So I think I've made a horrible mistake, and I got to fix it. I think when it comes to the other non-linear blue curves, here's what's really going on. Hold it. Let me put my isocline back in. Now, the isocline itself is indeed one solution. But look at this solution up here in blue. I think what has to happen then is I have to come in and hug that isocline arbitrarily closely as an asymptote, an oblique asymptote, but not quite touch it anywhere. Even with the solution down from below, I think I got to come in asymptotically to that isocline and never quite touch it, otherwise I'd violate the existence uniqueness theorem. What do you think? Where are you on the scale of happiness? Yes.
Why is that true?
I cannot prove it to you, I'm sorry. Actually, this is one of the theorems that's well beyond the scope of the course. However, you got to notice something interesting about this theorem. This reminds you guys a lot of Cheever's. What have you had in the past? You've had the intermediate value theorem, extreme value theorem, the mean value theorem for both derivatives and integrals. And they're all examples of these existence theorems. We tell you something has to exist, but we don't tell you what it is. And this is another one of those types of theorems. And I apologize, but if you open some advanced level mathematics course, book, text, you might be able to find such a proof. But it is beyond the scope of the course. But I'm afraid, you guys, I'm sorry if that sounds nasty, but I expect you to know the theorem, the punchline, the result. What do you think? Anybody? What does my question really ask? Thank you. I'm just looking for the one solution to my differential equation passed through that one point. So when I close my eyes, I shouldn't say close my eyes. When I open my eyes and plot that point 1, 2, right there. I'm asking you to draw the solution that passed through that point. I guess it looks very similar to the blue one I just drew. Very close to it. Got lucky. So there's the one trajectory or solution to the DE passed through the point 1, 2. Nothing more.
It's too hard.
You're being facetious, aren't you? I hope. You guys just don't wanna play?
It exists.
Doesn't? Anybody? What can I say about the solution this DE passed through that point, negative 3, 0? I'll wait.
But you have to figure out whether or not it exists before you can even
Okay, if you
conclude anything
exist.
about it.
I'll do it. My function f in two variables is simply what y prime is equal to, and that's just x squared plus x times y to the 2/3 power. I want a yes or no answer. Is that continuous everywhere?
Yes.
I agree. Now, if I were to look at the partial of f with respect to y, I think that's just going to generate a 2/3 times x times y to the negative 1/3. I want a yes or no answer. Is that continuous everywhere?
No.
No. What do you mean no? When? Was it not continuous?
Y to the negative 1/3 is equal to 0.
Or how about when y is equal to 0? But through that point, I think y is equal to 0. And so I think this partial for f respect to y is not continuous about any point at x equals 0, when y is equal to 0, excuse me. So look at my theorem. Look at it carefully. Look at the English. What the heck can I possibly conclude about the existence of such a solution?
It doesn't exist.
There's no one particular solution.
No, we didn't understand my question. I asked, what can you conclude using this theorem?
Not all the solutions are unique.
What's that?
Can't conclude anything because it doesn't meet the requirements.
Beautifully put. I think with this theorem, I can conclude absolutely nothing. Look at what the theorem says carefully. It says, gotta eat you like this? If both these are continuous, something happens. But if one of these conditions is not being met, this particular theorem doesn't say anything. It's inconclusive. I may have a solution, and if I do, it may or may not be unique. I don't know. My point is, this particular theorem tells me nothing about the solutions this DE passed through this point. It's inconclusive. The only way this theorem could say anything about such a solution is if both these conditions are indeed being met. Do you guys see my point? It's subtle, but it's important. Man, I've got 7 minutes. Ay, ay, ay. That displeases me to no end. Because I can't come up with a sophisticated example in that short period of time. Do you guys think we could do something a little different today? Only because I'm kind of stuck. I want you to have a few more examples under your belt. Can I just give you a sophisticated example? Maybe you can just play with it if you have time. And I promise I'll pick it up tomorrow. And I won't assign anything on this. Okay. You know what? I don't want to make it up out of thin air. Just so it works nice. I did make up some examples. This is math 12. Oh, look at that. Beautiful. Actually, in case you guys are interested, it's up to you. I'll give you a few. Here's what I really want to discuss tomorrow. Well, I meant to do it today. I think these are more sophisticated. So can I have you guys take a peek at our problem trajectories? Oh, jumping back to the very first section, 1.1. Take a peek at these. How about 15 through 24? Let's do all of them. And then take a peek at 26. Just let me know how to go. I don't want to talk about it. Yeah, all the way back to 1.1 was the topic of orthogonal trajectories. I did not mention in class yesterday.
Does that mean we're